Okay. So for anybody else who's feeling a little down, I have memes, so hopefully they make you laugh. Um, my first one, if anyone's a fan of Avatar, The Last Airbender, procrastinators most of the time versus procrastinators 30 minutes before an assignment is due. I 100% this was me. I pulled three all-nighters in like the last week and a half. So, hi. I'm like the worst procrastinator ever, which I think is ironic because I always tell you guys don't procrastinate, don't save your assignments till the last minute. I don't practice what I preach, but sometimes you get your best work done when you're under pressure. So, you
Yeah,
know,
that it works. Yeah, it works.
it does. Unfortunately, I feel like if it didn't work, that would be what would encourage us to not procrastinate, but I don't know.
I was
Um,
preparing for this exam for 3 weeks and I got 64. Night before, 80%.
yeah. Oh, here's my next one. Baby Yoda is like a mood all the time, but fitness instructor. Have you ever done a marathon? Me, like on Netflix? All the time. Oh, show of hands or reactions or something. Has anyone watched Squid Game? I won't ruin it for anyone, but it was so good. I liked it at least. Yeah. The memes from that are very good too. We've got some very creative people in the world. All right. And then my last one, just in case you wanted to have this fact live rent free in your head for the rest of your life, your nipples are older than your teeth. You need to take a second to think about it, but it is true. Anyways, yay. Good memes. Um, okay. So this week we are talking about t-tests. We're module six out of 10. So we're more than halfway done with the semester, which is really exciting. Pretty much from here, we have ANOVAs, which will take like a week each. And then we have two-way ANOVAs, kind of mixed in with one-way ANOVAs. But ANOVAs are like the last major tests that we have. And there's combined 5 tests total, but there's a lot of crossover between all of them. And a lot of the concepts from T tests end up crossing into ANOVAs. But this is the last lecture that we have before exam 2. Hopefully that wasn't a shocker to anybody. Uh, but uh, next week we'll have a review, which I emailed everyone about over the weekend. And I might have to just do a recording next week because I might be traveling, and I would end up being stuck at an airport during review session, which I'm not sure we want airport announcements in the background. So um, I will update you guys on that on Wednesday when I hear back from some people. But this will be the last lecture. So next week is a review where just whatever's from this week at activity 6, discussion 6, and quiz 6 will be due next Monday. And then next week is just review of correlations, regressions, and t-tests. And there will be like an extra credit quiz similar to the last exam. And then the following week on the 25th will be your second exam. Similar format. I'll go through all of that next week. And then you have the rest of that week to chill out and then have a great time on Halloween without worrying about turning in anything the next Monday. So, yay! For any of you who like spooky season, get wild. But make good choices. Always make good choices. Yeah. But anyways, that's kind of like a rundown of where we're at in the semester. I feel like we're gonna come to a close pretty quickly. So study, study, study. But this week we're talking about t-tests, and I have 3 slide PowerPoints. That's what they're called. I have 3 PowerPoints today. This first one is kind of just going through the fundamentals of t-tests. And then the second two are just a rundown of SPSS outputs and how we set stuff up and how we interpret things, etc. So those ones will go by pretty quickly. But to give you an idea of where we are in our decision tree, the last couple of weeks we were focusing kind of in this upper part of the tree where we had both parametric dependent and independent variables. And if we wanted to look at the relationship between those two variables or multiple independent variables with like a dependent variable, we did a correlation. And then if we want to predict a dependent variable using independent variables, that's when we use the regressions. So that's kind of like the first major chunk of this next exam. The second chunk is going to be t-tests. So we're kind of following this pink-red pathway here. So we'll still have a parametric dependent variable, but now we're going to have a non-parametric independent variable. Usually this is going to be nominal. We'll only have one independent variable, and it's only going to have two levels or two categories that it can be split up into. From there, it's just determining if we have a between subject factor or a within subject factor, and that will tell us if we are running an independent or a paired t-test. So these are the only two t-tests you guys are required to know about this semester. There is also like a single sample or a one sample t-test, which you'll probably see when you start going into like the analysis in SPSS, but we don't really work with that one. So only two tests to remember, which puts your total test count at about 5 for the second exam. If you're not, well, it'd be 4, yeah. If you're not counting like bivariate and multiple differences for the correlations and regressions. But if we kind of like pop this into its own flowchart, if you like viewing things a little bit differently, the type of data we have is parametric or ratio / interval dependent variable. There's only going to be one. Sometimes you can have multiple, but that starts getting into a different type of test later on. So for all of our examples, we'll only have one dependent variable for t-tests. Our independent variable should be nominal. So similar to the last couple of weeks for your discussion this week, you'll be coming up with some type of research question that's centered around making up, you know, a study design that's related to the field of kinesiology. So, or that you would end up using a t-test on. So when you come up with your dependent variable, it should be ratio, independent variable should be nominal or categorical. You only have one independent variable. It has 2 levels or 2 categories. When we end up with 3 or more categories, that's when we go into ANOVAs. So that's why I was saying like the crossover in concepts is pretty nice between t-tests and ANOVAs. So hopefully by the time we get to ANOVAs, it's not going to be super foreign to talk about stuff. But from the 2 levels, we can either have a between or within subject sample for that independent variable. If we have different samples for each category, then we end up with an independent t-test. If we have the same samples that are measured twice for our independent variable conditions, then we end up with a paired samples t-test. This is also referred to as like a dependent t-test. So I think the Laird Statistics website refers to it as a dependent t-test. So there's that. But SPSS, the independent t-test and paired samples are kind of like the fairly consistent terminology that shows up throughout the software. So the goal, based on the design that we have, this is the first test that we're going to be looking at where we have a cause and effect. So we have some manipulation of an independent variable. Usually we'll have an experimental group compared to a control group. And then we want to see how the manipulation to the different samples affects the dependent variable outcome, right? So Mainly, we're looking at differences between two means in particular, where we take the mean of one independent variable grouping and we take the mean of a second independent variable grouping, and then we compare them together to see if they are significantly different or not. For statistical differences, we evaluate this by looking at a t-statistic. This is also referred to as a t-score or a t-ratio. I try to stay consistent and either just refer to it as t-statistic or t. And the way we calculate this is by looking at the mean difference. So if we have 2 samples for all t-tests, we look at the mean of one group minus the mean of the other group mean, right? And then we divide that by the standard error of the difference. So this is going to be calculated differently depending on the type of t-test you're running. So whenever I ask you guys to calculate t, I'll always give you 2 means and the standard error of the difference. So you'll always have at least those 3 variables to calculate t. I do want to point out, and I think I write this later in the slides, but the difference between these 2 means should always be the absolute difference between them, or the absolute value of the difference. So that way, if you have like a small mean for sample 1 and a large mean for sample 2, that difference would end up giving you a negative number. If we end up taking the absolute value of the difference, then it's just, this is the value of the difference between 2 means, regardless if it's positive or negative, and then the negative doesn't end up affecting our t-statistic. Because everything, well, at least when we start looking at the t-table, which is like a couple slides from now, none of the values in that table are negative, and it can be confusing because if you look at it and you're like, well, of course, if I have a negative t-statistic, then it's obviously less than what's in the table, but that's not the reality. So whenever you calculate t, just make sure you're doing the absolute value of the mean difference. So that way negatives don't affect your t that you end up calculating. But this will be calculated using your raw data. So if I gave you like 2 sets of groups, you could calculate the mean for each, or I give it to you, you get the standard error, and then ta-da. Okay. But again, this is for both between and within subject design, so both for paired and independent sample tests. The null hypothesis for t-tests, the research question is usually going to be investigating if you have a significant effect on a dependent variable based on some type of manipulation. And again, you'll want to look for an independent variable that has 2 levels. So either individuals are going to be going through 2 conditions, or you're going to be splitting people up into 2 groups, and each group goes through 1 condition each. Our null hypothesis then ends up being that the independent variable has no significant effect on the dependent variable. Another way you could word this is that the means are equal to each other. And then our research hypothesis is just the exact opposite of that, where we say there is a significant effect or the means are not equal to each other. In terms of like the interpretation, when we run our statistics in SPSS, we'll still get 2-tailed p-values. However, when you interpret the p-values, sometimes it is acceptable to say like, oh, well, this group ended up with a higher, mean value of this dependent variable compared to the other group. Usually we reserve that for like 1-tailed tests, but it's not uncommon for people to start inserting directions into the research hypothesis. So I won't, fault you guys on that for t-tests. It's just because you only have 2 groups that you're comparing. So if you start out with your statistics wanting to show, is there a difference or is there not? And then in your interpretation of the results, you're able to see what the mean difference is. based on how you subtract your variables and you argue, all right, well, this one was definitely greater than this one, and that difference just happened to be significant, that's okay to add in your interpretation. In the slides, if you're in the PowerPoint version of the lecture, there's some other variations that you can use for the null hypothesis in the notes section. So instead of saying like no effect, we could also just say there's no significant difference between the means of sample A and B, or the mean dependent variable of sample A is not significantly different from the mean dependent variable of sample B. Dependent variable being whatever the measure is that you collected. So yeah, there's a lot of possibilities with how you can write these. The one wording that I would be a little bit wary of is to make sure you're not saying there's no significant difference between the dependent variable and the independent variable. So if you read back your interpretation when you're writing these out in your activities, and you can input a difference between the dependent variable and independent variable, change your wording, because we're not comparing dependent variable and independent variable, we're comparing independent variable groups in terms of a dependent variable measure. So yes, that's just something to be cautious of, because it does impact the meaning of your interpretation. So just be careful of that. For our statistical significance, obviously we got to calculate some p-values. I had a student share this meme with me last year and I loved it. So I just wanted to use it at some point. But that one, when your p-value is less than alpha. Yeah. Anyways. For t-tests, we can determine p a couple of different ways. We can estimate p using a t-table, which is kind of similar to our z-score table. So this is the second table we're introducing this semester. But basically the way that works is you compare a critical value to the t statistic that you calculated a couple slides ago. And then the comparison of those two ends up telling you what your estimated p-value is at a certain level of confidence and a certain degrees of freedom based on your sample size. We'll get into that in the next slide. So if you have questions on that, hold it for a second. So that's for estimated p-values. We can also calculate exact p-values, which will be given to us when we run our tests in SPSS. So I go over how to interpret and where to find exact p-values when we go through the part 2 PowerPoints for the procedures for independent and paired samples t-tests. In terms of the evaluation of p, it's still going to be the same as how we've been operating the last several weeks. So when you have p greater than alpha, that means you accept the null hypothesis. So in a t-test situation, that means the independent variable has no significant effect on the dependent variable. And then if p is less than alpha, we reject the null hypothesis and we say that the independent variable does have a significant effect on the dependent variable. I'm using alpha just because when we look at the estimated p-values, we'll use the 90, the 95, and the 99% levels of confidence as examples in your activity. So I didn't want to just put 0.05 as the alpha because I didn't want to confuse anybody if you're referring back to the notes. For exact p-values, when we're in SPSS, our default setting is always going to be 95%. So whenever you're doing exact p-values, you could make a note that that's p is always going to be in comparison to 0.05 for SPSS. But for the t-table, the alpha can change based on the level of confidence that I give to you. So keep that in mind. But generally it's just, greater than alpha, accept the null, less than alpha, reject the null. That part hasn't changed. Do I have any questions so far?
One question about the groups, independent groups. And so we are comparing multiple independent groups versus one dependent variable.
So we have one dependent variable. That's like the measurement that we're taking. So maybe I want to see like, well, like we can take our class, for example. When we did the activity 2 and I had you guys do push-ups, let's say that our push-up data or how many push-ups a person can do is our dependent variable because that's what we measured. And then I want to see if there's a significant difference in the number of push-ups that people can perform based on if they're male versus female or if they're active versus non-active.
Okay, got it.
Yeah. So we've got 2 levels of an independent variable. So in that example, like active versus non-active would be 2 levels of physical activity status, or if we're looking at differences in gender, male versus female, those would be differences, or those would be levels of a gender independent variable. But in either case, we still only have one dependent variable that we're looking at the measurement of. So, yeah. Okay. Other questions before we keep going? Cool. All right. So the t-table looks something like this. You guys have a PDF version, so you can zoom into it. But again, we'll use the t-table when we're estimating p-values between the, or estimating p-values for the differences between 2 means, okay? So the way that we read this, we have to know a couple of things. The first thing is the level of confidence. And if we know level of confidence, we know what alpha is. So use that information, I guess. We know if you have like a 95% level of confidence, 100 minus 95, it ends up being what your alpha is. So you can look either at the bottom of the table with the confidence level, or you can look at the top of the table where we have our alpha values listed. Now, the one that you're going to want to look at is the 2-tailed row, because I know some students in the past have gotten confused where they looked at the 1-tail row, and that's not what they should have been looking at. So make sure you focus your attention on 2-tail row if you're looking at alpha. Personally, I like to look at the confidence level row at the bottom to figure out which column I should read, just because it's a little bit easier for me and less confusing. But you have to know the level of confidence, and then you also need to know the degrees of freedom. So remember we said, oh God, I think it was in one of the first lectures we did, but degrees of freedom is a way that we account for the fact that we'll never have an entire population measured. So in some ways, it adds a little bit of error to our final statistics to account for the fact that our samples always are smaller than population. But degrees of freedom for the t-test is going to be n, like our total n, the total number of people we've collected, minus the number of samples that we have. And I have examples of this on the next slide, which is why there's an asterisk there. But once you can understand or know what your level of confidence or your alpha is and how many degrees of freedom you have 2 bases to go off of. And then you can find in the table a critical value for T. And what this represents, let's say we were at a 95% level of confidence with 15 degrees of freedom. That would give us a critical value of 2.131. And what this value means is that if you think about the way that we calculate T, it's the mean difference divided by a standard error. So T is kind of quantifying or standardizing the difference between 2 means. And the critical value in the table is just telling us, given a certain degree of freedom based on our sample size and given a certain level of confidence, this value is how large, where's my mouse? This value is how large T has to be in order to be considered significant. So when we evaluate our calculated t statistic in comparison to the value in the table, we always say if t is greater than the critical value, then p is less than alpha, indicating that we have a significant difference between our means. Okay. I've heard students tell me a lot of ways that they decided to remember this, but I mean, use whatever way works for you. The signs are opposite, so I think that's like the easiest way. Most students think if they remember one, like t is greater than critical value, then they always remember p is less than alpha. But that would mean, like, if, using this example, where was I? Right here. If our critical value is 2.131 and we ended up calculating a t that was 2.5, we would say that our estimated p-value is p is less than 0.05, because that's the alpha that's associated with the 95% level of confidence. If we had a t that we calculated as 2, that's less than 2.131, right? Or that's less than our critical value. So then in that case, p would be greater than 0.05, or a non-significant difference. So that's how the table works. You guys will get to have several examples in both the quiz and the activity. I would definitely recommend doing the activity before the quiz, though, so that you don't waste your attempts. And then you get examples of like going through the table and how it works for different levels of confidence. So that's my little note of advice. But for the degrees of freedom, it'll be different based on the type of t-test that you are working with. So again, the general rule of thumb is we look at the total sample size minus the number of samples. So for an independent samples t-test, degrees of freedom is going to end up being our total n minus 2, because we have 2 samples. So if we had, say, one sample had 20 people and the other sample had 20 people, our total sample size ends up being 40. We put the 2 together, and then we divide by 2, or we minus 2, because we have 2 independent samples. For a paired samples t-test, we only collect 1 sample, and then we repeat the measurement on them multiple times. So in this case, if I had 20 people that I repeated the measurement on, my total n is 20. That's my sample, right? And then I subtract 1 because it's a repeated sample. Correct. So you'll use these values for the t-table. And it's just going to be based off, usually I'll say like, oh, this is a paired sample. And these are, the values for the means. These are the values for the standard error of the difference. This is how many people were in each sample, if there's multiple samples, and then you just do plug and chug into the formulas that I've already given you, and you can calculate t. You can figure out your degrees of freedom. I'll give you your level of confidence, right? And then based on that, you can find your critical value and then compare t to critical value, and then you can estimate your p, okay? So that's using the t-table for estimated p-values. The rest of our lecture is primarily going to be in exact p-values. I have a question in the chat. Do we need to run any pretest to identify which t-test to use? Great question, and the answer is no. So you can figure out based on the decision tree. I can pop back to that slide really quick. Pretty much, if you know that you have a single independent variable with 2 levels, and you know what type of sample you've used, you can figure out what t-test to run. So t-tests are largely determined by the study design and not by any like precursor testing information. Yeah. And then another question. For 2 independents and the sum of both, and then divide by 2. Oh, the divide, that was a misspeak. I think I corrected myself, but it'll be total number of n. So you sum the 2 samples together, and then, oh no. Well, that's rude. PowerPoint just died. But yeah, while I'm opening that back up, you take the sum of both sample sizes and then subtract the number of samples that you collected. So in an independent t-test case, it would be 2. And what happened? That's so weird. I think my computer's kind of had it with me today. This is where we're at. This is where we've gotten. All right. Well, now we've got the Wheel of Death, which is equally fantastic. So I guess we just have to wait for it to open back up again. I'm gonna drink more coffee. It is Monday. Good old Monday. All right. It's probably because I have too many windows open. I've been doing class assignments all day and adding stuff to your guys' class. So naturally, very overloaded computer. Come on, listen to my commands. There we go. Okay, now we're back at business. Where was I? Assumptions. Cool. So the assumptions for a t-test are going to be kind of similar to what we've been doing so far. We'll have random sampling on how we collect our people. We'll have a normal distribution, hopefully, and no significant outliers, particularly for the dependent variable that we've measured. When we were in correlations and regressions, typically we would have had to test for normality for both the independent and dependent variables because all of our variables are parametric. But from here on out, since we'll have nominal independent variables, the rule of thumb is that the normal distribution and no significant outliers is typically going to apply to the dependent variable measure only, because that's the only variable we can actually run those statistics on. So when normal distribution, this is based on the study design, these next 3. So sometimes I usually lump these together, but we'll have one dependent variable that's ratio data, one independent variable with 2 levels that's nominal data. And then based on our types of samples, that's where we kind of start to differentiate the rest of the assumptions for the test. So I've put like assumption number 6 is going to be specific based on the type of sample we have. So if we have a between subject independent variable and we've determined we're going to do an independent t-test, then our added assumption is the homogeneity of variance, which is tested using Levene's test. We'll go over what that means in the next slide. If we have a within subject independent variable and determine we're doing a paired samples t-test, then we have to look at normality and having no significant outliers for difference scores. So that's why I wanted to make the distinction that this assumption applies to the dependent variable measure, and then that will still be a consistent assumption that we have in coming weeks. For paired t-test specifically, we also have to look at normality of the difference scores. So don't get those confused. There is a question on your activity this week where I ask you to list the assumptions. So make sure that these 2, like if you're listing a paired samples t-test assumptions, that this is distinctively different from this assumption here. Okay. Because one's doing dependent variable, the other one's looking at different scores. For homogeneity of variance, this is for independent t-test only. tested with Levene's test. And it's automatically included in the output when you run an independent t-test in SPSS. So when you run the test, it will give you a p-value, which means if we have a p-value, we have a null hypothesis that we're assessing. So the null hypothesis for our homogeneity of variance is that the variance of each sample is the same. In other words, if we looked at the variance in sample A, it is equal to the variance of sample B. Or we can say it's relatively equal because sometimes they might be slightly different, but if they're not different enough, then we still can say we've met our assumption. So in terms of the p-values that you get for Levene's test, if you have a p-value greater than 0.05, that still means we accept the null, right? And if we're accepting the null and we say the variances of sample A and sample B are equal, that means we've met our assumption. So assumption tests, usually you want your p-value to be greater than 0.05 so that you can say you've accepted the null hypothesis or you've met the assumption. If we had a p-value less than 0.05, same thing goes, reject the null, which ends up meaning that the variances of sample A and B are not equal. And then that means we've violated our assumption. Keeping these two in mind, I'm going to skip to the next slide. This is what it would look like in SPSS. So I oftentimes have students who mix the p-value for Levene's test with the p-value for the t-test because they're in the same table. And it's important that you use the Levene's test first. That's why it's listed first, okay? But you have to make sure you've met your assumption before you know how to interpret the t statistics for the t-test, which are located in the other part of the table. Right, so p-value for Levene's test is here. P-value for our t-test is over here. And you'll see that there's two values. And this is the reason why you look at Levene's test first, okay? So if you'll notice these rows right here, one says equal variance is assumed and the other one says equal variance is not assumed. Okay, so if we look at 0.174, that is greater than 0.05. So in this case, we would say we've, p greater than 0.05, we accept the null hypothesis. We've met our assumption that the variances between each of our groups are equal. And then that would tell us to read the equal variances assumed row. And then we would be able to determine what our p-value is for our t-test. Okay. If this was less than 0.05, then we would read the equal variances not assumed row. And this would be our p-value for our t-test. Okay. Question in the chat: what happens if the variances are not equal? Basically, what happens is there's a correction factor applied to the degrees of freedom. So you'll see here we have 38 versus 35.05. So that correction factor ends up allowing the variances to equal out. And a lot of times you'll have unequal variances when you have unequal sample sizes. Not always the case, but basically that's what happens. So you can still accept the p-values even if you reject the null because SPSS automatically applies the correction for you, which is nice. Yeah. Okay. If we were in a paired t-test situation, oh, hold on, sorry. Do we need to do anything to the data? No, you do not. All right, so whether you accept the Levene statistic or reject it, you just read what the table tells you in the proper row. And that's it. Nice and simple. Yeah. All right. So that's for independent test, for independent t-test. If we're in a paired t-test, we have to look at the normality and make sure that we don't have any significant outliers for the difference scores. So there is a way to calculate the difference scores in SPSS, and it's by going to transform and compute variable. From there, you'll get a box that says target variable, which it's the name of the new variable that you're creating, so we can just call it difference. And then the numeric expression section is going to be how you're calculating the different scores. So the textbook, as well as the Laird Statistics website, they recommend doing the experimental group minus the control group. And I'll, like, in the grand scheme of things, it doesn't really matter which order the variables are in, because if we did like experimental group minus control group and got a positive outcome, and then switch that into control group minus experimental group and got a negative outcome, every value or every different score is just going to be a reciprocal of the other way around of doing the math. So as a rule of thumb, you can just remember experimental group minus control group. But if you forget this, it shouldn't make that big of a difference in your analysis. But that's how we would set this up. And then we would press OK. And then we end up getting a variable added to our data view. And then from here, we can just do a regular test for normality with an explore analysis. And then in the next, one of the next PowerPoints, we go into we're going to specifically look at the Shapiro-Wilk test for normality, and we'll specifically look at box plots for outliers. That way it's the same for everybody, since we've done a lot of different ways to test normality. But that way it's less subjective and more like, this is what we do. Make it easy to remember. Okay, so that's the assumption for our paired t-tests. And then the other thing we'll be doing this week is calculating effect sizes. So we kind of hinted at Cohen's d effect size back when we talked about sample size analysis and power analyses, where I typically gave you an effect size that you had to stick into the G-Power program, and then you would, get your sample size or power out of that. Now we're actually going to calculate it using the descriptive statistics that we get from our output. So for independent t-tests, we're going to use the group statistics, or the normal descriptive statistics that pop out in our output, which is going to have our sample sizes for each group. It'll have our mean for each group and our standard deviation for each group. Those are the only three values you're really interested in, or the three variables. And Cohen's d is looking at the mean difference divided by the pooled standard deviation. Again, the mean difference being the absolute value of the difference, so that way the negative doesn't impact anything. And then the pooled standard deviation is this nice, fun, big thing here. So this goes in the denominator. And I separated them because when I put it in the denominator, things got very, very small and it was just really hard to read. So what this is S1 is a standard deviation of group 1 squared. So that's what S12 means, S1 squared, times the sample size for group 1 minus 1. So that's one chunk. And then we add it to the same product for sample 2, and then divide by our degrees of freedom. So total n, right? N1 plus N2, or sample size 1 plus sample size 2 minus 2 is our degrees of freedom. And we take the square root of that and then do the mean difference divided by the pooled standard deviation. So if we're using numbers just to kind of plug and chug and put things into perspective, right? I rounded to 2 decimal places so I could fit all of this on the slide. But we take the absolute difference between the two means, and then the square root of our standard deviation of sample 1 squared times the sample size minus 1 plus the standard deviation of our second sample squared times sample size minus 1, all over our degrees of freedom. And then we end up getting an effect size of 0.346. So once you get your effect size, then you have to interpret what it means. And Cohen's d effect sizes, this is kind of a general guideline that you can use, where if you have a value of 0.2 or lower, generally we say that's a small difference between the means. Anything around 0.5 is considered a medium difference, and anything 0.8 or higher is a large difference. So this kind of falls between a small and medium strength Cohen's d. So I would say because 0.346 is kind of closer to 0.2, that we would say it's a relatively small difference between the means that we've observed here, which makes sense because the actual mean difference is, tenths, like 0.3 something, right? So it's not that big. But effect sizes are helpful or meaningful to our data because they tell us how large the difference is that we're actually measuring. So you might have a very, very, very small mean difference, but it ends up being significant. Or you could have a very, very small mean difference and it's not significant. So it's kind of like a little added boost to the interpretation of your data when you have an effect size paired with your p-value. The calculation for effect size is pretty much the same for paired t-tests. We just pull the information from a different place because SPSS calculates it for us. So in this one, we've got paired differences in our paired sample t-test. And this is the mean difference divided by the standard deviation of the difference. Or you can think mean difference divided by standard deviation if it's easy to remember in that respect. But the mean difference should be the what is it? Subtraction doesn't have a fanciful word for the answer, I don't think. But this will be like, this example was a carb and protein drink and versus a carb only drink. And so the carb protein drink minus the carb drink ends up giving us a positive mean difference, which indicates that the carb drink had a higher value or a higher mean than the carb drink, right? So carb protein greater than carb, which is one of the things I was telling you guys earlier, is you can actually specify which mean was greater than the other one when you do your interpretations. But oh, that's weird. The same thing goes. That's not supposed to be over there. I don't like that. What the hell? Anyways, this was supposed to have our effect size table, and I'm not sure why PowerPoint is freaking out. But if we plug in our numbers from our table, the mean difference divided by standard deviation of the difference, we end up with an effect size of 1.42. And that would be greater than 0.8, which means it's a relatively large difference for this particular example. Okay. Any questions on this stuff so far? All right, so I'm gonna stop sharing. We'll switch gears.